Hello, everyone. Welcome to this talk. I'm Sujoy Dutta from Bloomberg. Today, I'm going to talk about a very practical problem we ran into in our ML platform, the GPU job scheduling latency, and how we predicted it. So a quick introduction about me. I'm a senior software engineer in Bloomberg. I work on the infrastructure that powers the ML workloads, especially the GPU-heavy training jobs. So here's the roadmap. We'll start with a real user pain point, and then we'll dig into why our first solution didn't work, and then I'll show you the design that we landed on. And we'll also go over some of the learning lessons and how it is being used right now. So consider this scenario. A user submits a PyTorch job at 10:30 a.m., and then at 11 it is pending. They grab lunch and they come back, and it's still pending. Finally, it gets scheduled at 2:30 p.m. So the whole time, they were having no idea whether it is just about to start or whether they could cancel it and resubmit it. And in many cases, they tend to do that as well. Like they would be impatient and they would be just canceling it and resubmitting the same request with the same number of GPUs. So that uncertainty, that's what the experience we wanted to fix for our users. So users need ETAs to plan their runs and their pipelines. So when users can't predict the wait times, they tend to do the irrational things. So they over-request the GPUs, they submit the duplicate jobs. And for us as the platform teams, we had no signal that the queue was backing up until the tickets started coming in. So the users would file into our platform tickets saying that, hey, my job is already queued up for this amount of time. Is it going to start now? What's the ETA, etc. So when we received the users' tickets at that point, we were then reactive, trying to clear up if some old jobs will need to be deleted or if this job needs to be prioritized. So we were being reactive instead of being proactive. So before we talk about the latency prediction, let's quickly take a look at how the job actually gets scheduled in our system. So a user submits a job through Kubeflow. In this example, a PyTorch job requesting, let's say, 3 GPUs. So Kubeflow creates the underlying Kubernetes resources. However, before the request reaches the cluster, the workload goes through the job scheduler. So we use Karmada for our multi-cluster job scheduling and orchestration. So the scheduler evaluates the available clusters. So here in this example, let's say cluster A and cluster B are available in that tier. And this job scheduler would be looking at the GPU capacities, it will be looking at the policies, constraints, and then it decides for this incoming job, what would be the best fit cluster. So here in this case, if the job had requested 3 GPUs, so cluster A tend to have 4 GPUs available for the user's job. So the job scheduler would go over all of these constraint details and the GPU capacities, and then pick the cluster A for the user's job. So the availability of the GPU and the time taken to schedule the job can introduce that GPU job scheduling latency. So here was the core insight for us. We already had the data. So every time a training job, a PyTorch job runs and executes, we capture its job execution time, the various timestamps, and all the metrics associated with that particular job. So the first solution, obvious solution we came up with was running some batch jobs to get this aggregated data and compute the average as a batch job, maybe overnight. And we would already be computing that GPU latency. But this was happening as a batch job. So at the end of the day, the computation of average times was calculated. But when we looked at the real painful waits, the 60-minute, 90-minute delays, they weren't happening randomly. So they were happening during the spikes. The GPU workloads tend to be quite bursty. So you can think of like if everyone is trying to submit a job during morning hours, all the jobs are requesting X amount of GPUs almost at the same time. So that's like a peak period for us. Then the spike could happen again at some other point of time in the day. So the spikes do happen, but if we compute just the average from previous data, the spikes tend to get hidden because the average smooths it out a little bit. So that's when we realized that we didn't need more data to solve this problem. we needed live signal. Not yesterday's metrics, but just today's traffic. Even so, like last 1 hour or so. So like I mentioned, the daily averages smooth out the exact spikes. So we need to be like more real time. We need to see what was happening in that job scheduler within that last 1 hour or so. So for us, the Karmada scheduler also helps in making that live system state decision making and not just the historical summaries. So another insight was not all jobs weigh the same way. So one GPU job can fit in almost anywhere. So it could fit in cluster A, B, because almost all the clusters have maybe 1 or 2 GPUs left. So the one GPU job can find a slot very quickly. However, 8 GPU job it needs a chunk of a node. So, and a 64 GPU node job can need multiple nodes to become available at the same time. So there is that difference, like how a one GPU job goes in, it may find its own time slot very quickly, whereas a large request can find some time. So if we were to average and put one GPU request, 64 GPU requests together, average, and give out a single number out, that would make the prediction sort of meaningless because, like I was mentioning, the one GPU job might get a pessimistic ETA because we are averaging it out with a higher request, whereas a 64 GPU job might get a very optimistic one. Both would be incorrect for the user's incoming job. So what we did was we bucketed them. We bucketed them into 3 tiers, and I'll talk a little bit more about it in the next couple of slides also. So we bucketed them into 3 tiers, small, medium, and large, and each bucket has its own rolling average. So a small bucket, you can think of one GPU jobs tend to be like a very quick job, let's say a fine-tuning job or small embedding task. This would be requiring one GPU job and they would go in much faster, whereas full training could require like multiple GPUs. So we will be categorizing anything that is larger than 10 GPUs as a large buckets. Everything else was categorized in between in medium. So these tiers were defined at the start of the whole process. So these were defined by us. And we are working towards a system where we want the bucketing happen dynamically. And I'll talk about it in a bit. For now, like the simple bucketing strategy into the 3 tiers was effective for us to give a more closer and almost correct estimated GPU latency for our users. So what do we actually measure? So once we had the buckets, we needed a clean signal. So the clean signal comes from the scheduling object. So once the job scheduler receives the user's request, it creates up the object, and in that object has a lot of properties. And the main property that we were looking at is 2 timestamps. So at the creation time, when the job enters into the system, a timestamp created is assigned to that particular scheduling object. And then there is another timestamp, which is the last transition timestamp. So the last transition timestamp is when we are actually trying to capture the moment where the scheduler is moving the job from pending to the scheduled state. That means the scheduler, as it was making a decision whether cluster A or B has enough resources, after a while, let's say one cluster, let's say cluster A got the resource opened up, the scheduler would move it from the queue to the actual cluster for execution, and that transition time is what we would capture in the last transition time. So the difference between those 2 timestamps is the queuing latency. And we track it per bucket. Like I was mentioning, a small GPU job may have a different sort of requirements, and we shouldn't be considering it in the same group as a large GPU job. So we try to get that particular queuing latency per bucket. So the number or the signal that we calculate as the delta is the signal we care about. And that's the raw GPU latency for a particular job. So to make our predictions real time, what we did was we kept a fixed size bucket, or you can think of like a fixed size window, say last 100 latency samples per bucket. So this is dynamic, and maintain a running sum. So the maintaining the running sum helped us avoid recomputation of all the X amount of jobs every time from the job store. So when a new sample comes in, if the window is full, what we do is we subtract the oldest value from the sum and drop it. And when we add the new value comes in, we add it to the running sum. So the average is then just divide this running sum by the size of the queue at that point, and which is not absolutely like 100% going to be accurate, but it averages out to be the correct time for the particular latency for that particular tier and bucket. So this gives us that constant time update that we need at the very instant user is submitting job, because we don't have that luxury to go back and calculate the batch compute at that point. And yeah, and just to be clear, we are not removing the job from the job scheduler. We are only considering this part of it for the rotating latency measurements. So this is purely for the latency prediction. So this is the user experience delta. So on the left side, users were before anxious, constantly refreshing, submitting duplicate jobs, requesting the same amount of GPUs, and wondering like if the scheduler is broken, why their job is not getting submitted, what is the delay. And after we started publishing this latency value back to the user, they were having more information. Okay, so let's say like the job is taking 14 minutes, so they don't need to resubmit it. They can switch back to something else, or even 47 minutes or some other number. They can context switch to do something else. But one thing to notice is the underlying same infrastructure, we have the same Kubeflow supported cluster, but now it is communicating back to our users. They are able to see what's happening and how much time it may take approximately. So we didn't eliminate the wait, but we eliminated the uncertainty, and that predictability changes the user behavior. So one gotcha we hit at the very beginning was what happens when the controller, which does all this calculation in memory, restarts. So the rolling queues are currently in memory, but when the controller is restarting, those values are lost, which means like the first few prediction after the restart has happened would be incorrect because we would have no data in it. So we added a hydration step to fix that. So on startup, we query the internal job data, which I was mentioning earlier, just for the last hour of raw latency sample, and replay them into the rolling windows. So it takes about only a very few seconds, but we have some data representing the cluster status from last 1 hour. So we try to maintain the continuity, and instead of giving a value of 0 seconds latency to our users, we are able to still get the last cluster state 1 hour ago and give them some meaningful prediction. So let's look into like how we make this particular value available to our users. So what we actually publish is 3 main metrics. So the first is the raw latency. So as I was mentioning, the delta between that creating timestamp and the last transition timestamp. So that is the raw latency, and this is our ground truth for every single job. So it is useful for tail analysis for us as a platform team to see like how the jobs are doing on the latency and set up some alerts on our systems just in case if something is going wrong. But it is used mostly for the tail analysis and the debugging purposes. Second, the rolling average. So this is the important one, the rolling average per bucket. And this is the ETA or prediction signal we expose to our users. So it reflects what's the average GPU latency for their job in that particular bucket in that tier. And the third is the pending count. So how many jobs are waiting right now to get assigned a cluster? So these are incoming jobs which have not found a cluster yet, but the user has already submitted a request for it. But they are all sitting in a pending state. So it will be useful for us as platform team to know how backed up our queue is. So we tend to keep this information also in this particular metric, which is the pending count. So all of these metrics feed into our dashboards and other systems which can consume from there. And we also set alerts when particular average latency crosses a certain threshold, so that we know that the queue is backing up rather than users reaching out to us first and saying that, hey, where is my job? I would be able to tell them that, okay, we are aware of it, and they can do so and so to remediate or submit their job sooner. So let's zoom out and try to put it all together. So a user submits a PyTorch job with the GPU request, let's say. It enters the scheduler, and they eventually transitions from the pending state to the running state or executing state. So in our system, the controller which I was mentioning is tracking the resource binding object. So that is the scheduling object. And the controller watches it transition. So when the exact moment of pending to schedule happen, we compute that queuing latency. So that latency sample is then pushed into the rolling window for the appropriate GPU bucket size. And the rolling average updates almost instantly because of that constant time calculation for that particular tier or the bucket. So from there, we have finally the two outputs. The first one is the publishing the matrix. So we publish the raw latency, the average latency, and for ours, we try to see the number of pending jobs. And then eventually, it is sent to the dashboards and for alerting. The second thing we publish is at the submission time, what happens is users want to get a response back immediately, right? Like they want to see what is the latency for their job immediately at the time of submission. So we try to give them that approximate average latency, which needs to be accurate by using a webhook. The webhook reads the current rolling average from that particular cluster and the tier, and it sees that, okay, this is the approximate ETA because the average calculated value is available. And so the user sees that estimate immediately when they submit a new job request. So it's a simple feedback loop. Measure the present and then update the signal and then expose it back to our users in real time. So we try to avoid doing any batch computation at the time of job submission so that there is no further delay and no forecasting jobs are used. So it is currently just event-driven and updates the job directly after the job is submitted. So what did we learn during this process when we were implementing this solution? So first, exactly once processing. So without careful predicates, as I was mentioning, there is the timestamp, the last transition timestamp. So every status update on that scheduling object would introduce a new scheduling value because sometimes an annotation gets added or something else happened, the last transition timestamp could change. But we don't want to capture all of those transitions. We want to capture only once the transition, and that is from pending to the schedule. And we make it happen using predicates. The second learning point for us is the buckets over the precision. So yeah, a general question could be like, we only have, let's say, 128 GPUs, so we could just assign one in-memory queue for the latency calculation for each GPU, right? Like GPU 1, so all the jobs with request 1 GPU can have a separate queue, 2 can have a separate queue, etc. But for us as the platform team, that would be a cardinality nightmare. So we decided that we have to summarize it or categorize them a little more efficiently. So on our side, the 3 buckets turned out to be sufficiently relevant because we had some analysis done on the past submission behavior of our users of various GPU jobs. So the small, medium, and large category sufficed. And the third learning for us was the cold starts, which I was mentioning that at the time of a deployment or a crash, the in-memory queues could get wiped out. So we learned this hard way after a deployment wiped out our in-memory windows. So this was also a great learning experience for us at the early stages of implementing this solution. So with this information, where are we going next? First, we do want to come to a smarter bucketing system. Rather than we defining the buckets in a static way as small, medium, large, we do want to have dynamic boundaries, which could shift a little bit on the real job submission data. So if there was 2, 3 GPU jobs also behaving similar as a 1 GPU job in terms of latency, we do want that boundary to be a little more dynamic. We would like ideally for the data to define its own segmentation. Second, this is the correlation for us as platform users. When latency spikes, why does it happen? What's the cause of the latency spike? So is it the workload pressure, or is it a draining cluster, or could it be some GPU health issues? We want to correlate that latency with the cluster state and the health events. And finally, the holy grail, the recommendations. So not just like, here's your wait time. We do want to move to to a state where we are able to recommend back the users what would be the ideal state. So if you request, let's say, 5 GPUs instead of 8, you will start 20 minutes sooner. And that's actionable for the users, not like a 20-minute wait time for you. So we want to provide some actionable insights to our users as well. So we are exploring our current latency data. We have all the events from the past, the job submissions from the past, and the latency that we have predicted for our users. So we are generating this historical data set, and along with some job completion signals, we are building the predictive models that incorporate all of these variables and features. So we want to move from the visibility to the guidance state. So yeah, so next time you see something pending, you'll know like there is a better way. And with that, I would like to conclude and open up for questions.
Thank you. Okay, we have time for a couple of questions before the break. Does anyone have any questions? Anyone? Okay.
Hi, Sujoy. Thank you for the talk. So I was just curious, since you have Karmada in your design, and Karmada recently has a new feature with priority scheduling, how do you see that play into solving this problem of GPU latency and scheduling jobs?
Yeah, so I think the priority scheduling, I think, is a very new feature. So at the time we had this initial V0 or V1 version of our calculations, we don't account for the priority scheduling. But I can see the situation could be like when a user requests for a priority job, we would have to kick out some already running jobs. So in that scenario, what would happen is we would have to remove that latency for that job. Because when a running job was submitted into a cluster, we accounted for its latency in our average GPU latency calculation. So we will have to update it dynamically at that point if a job gets kicked out and update our rolling estimate. And for a new incoming job, the latency probably will not matter, because if it is assigned as a high priority job, we can probably say that, okay, this job needs to get into our cluster immediately. So we would be taking that job and submitting it. Yeah, thank you.
Okay, we have a break, and I'll see everyone here after that. So enjoy the coffee break.
Thank you.